In this video, we are continuing to talk about optimization questions that involve a constraint. And we will do an example where we minimize a multivariable cost function by substitution. So the example says you are designing a rectangular box drawer that's open on the top. The material for the decorative front costs 5 cents per square inch, and the material for the other sides costs 3 cents per square inch. If the drawer's volume must be 1,000 inches cubed, part A asks, find the dimensions of the cheapest possible drawer you can design. And then if I scroll down, part B asks, what is that cheapest cost? So this question talks about a geometric shape, this rectangular drawer. So we can begin by drawing a picture. So let us draw a picture. All right, so I'm going to draw a rectangle for the front. And now I got to make this look 3D. So I got to make a 3D rectangular shape. So I'll draw a slanted line here, a slanted line here of the same length. Connect them. So this is making the right side. And then let's draw a slanted line here, starting to make the top. And then a line connecting these. And then for the lines I can't see, let's draw dashed lines. So from this other corner, dashed line this way, dashed line up to this top back corner, and then dashed line over to this side. And we have this rectangular box shape. So this is our drawer, and the question says that there's an open top. So there's no material placed on the top here. The top is open because we have to put clothes or whatever goes in this drawer. And the question says that the front, maybe this is the front side, the front costs 5 cents per square inch, so per inch squared. And it's going to be helpful to label the lengths with variables. So maybe I'll call this length x, this length y, and then this vertical length z. Okay, so now we are ready to set up a function for the quantity that we want to maximize or minimize. Recall that we call that the objective. So because the question is asking about the cheapest possible drawer, we want to minimize the cost. So I need to set up an equation for the cost. It is my objective to minimize the cost. So for the cost here, there are several sides we need to find the cost of. There is the cost of that front side, the decorative front. There is the cost of the back side. So the cost of the back side. There are the cost of the left and the right sides. So the cost of the left. I'm going to put that in quotes because left, it's got to be clear from context. This is my left side over here. Left side. Okay, and then there's the cost of the right. Cost of the right side. And finally, there's the cost of the bottom. So I'm going to do one of these costs slowly, and then we'll set up the rest of our cost function a bit more quickly once we have the idea. So for the front side, I know that it costs 5 cents per square inch. So I know I'm going to need to take that price, 5 cents per square inch, and multiply that by the area of the front. The area of that front side. Okay, so this gives me 5 cents per square inch times, and what's the area of the front? Well, it's a rectangle, and I know that the length is x, and the height is z, so xz, and the units of length. Well, I know here we're using inches for the costs, 5 cents per inch squared, and the other cost was 3 cents per inch squared. But I noticed this question gives me information about the volume as well, and that's also in inches cubed. So let's continue to use inches. Okay, so this area would be in inches squared, xz inches squared. So when we multiply these inches squared cancel with these inches squared, and we'll end up with 5xz, and the units are now cents. And that makes sense. We wanted this to be the cost of the front, so it makes sense that the cost is in a unit of money. All right, so let's write out the entire cost this way. So the cost of the front we now know is 5xz. For every other side, the cost was 3 cents per inch squared. So for the back, for example, we would multiply 3 cents per inch squared times the area of the back. And the area of the back is the same as the area of the front. It is xz. And now we need the cost of the left. So the left side is also costing 3 cents per inch squared. So I have to multiply that price times the area of the left side. The area of the left is yz. Similarly, the right is also going to be plus 3 times yz, because the area of the right is yz. And the bottom also costs 3 cents per inch squared. So I multiply 3 times its area. The area of the bottom is x times y. And we can simplify this. We get cost equals 8xz, adding the first two terms. Adding the next two terms, we get plus 6yz. And the last term by itself, plus 3xy. And that is our objective function, which is the cost here. Okay, so if I zoom it out a bit, the question tells me one more piece of information, which is the drawer's volume, and that fact that that's 1,000 cubic inches. So that is another piece of information that's giving me a restriction in this problem, and we call that the constraint. So the formula for volume of this rectangular box is going to be x times y times z, and we're given that that should be 1,000. So this is coming from the fact that the volume equals 1,000. That's where we're getting our constraint. Okay, so we have our objective, this cost function, that we want to minimize in this question. We want to find the smallest possible cost. And we have this constraint. So if we follow our idea of when we substituted before in our previous videos, we would isolate one variable in the constraint, equation, and substitute that into the objective. Usually we'd want to isolate whichever variable was easiest to isolate and then plug in. In this case, it looks like all of them are about equally easy. So after we did this, we would end up getting the cost in terms of two variables. Right now it's in terms of three variables, an x, a y, and a z. So then we'd have a two variable function. So to find its min, we could use our section 8.3 methods for finding extrema of two variable functions, and use the second derivative test to check whether our critical points are our local maxes, our local mins, or our saddle points. And I'm going to leave that as a homework problem. So in the next video, we will work out this same example, but using Lagrange multipliers. And we'll do that all the way through until we get a final answer.